In this video, we're going to introduce a much more challenging to describe problem, and that's one where we have a set of 5 different nodes, and these are connected together with springs. And if we stretch springs, of course, they will pull back together. If they're understretched, they'll push out. And what we have here are the natural lengths of the springs listed. So we have a length 2, this spring should be length 3, this spring likes to be length 4, length 5, and length 7. We can already see that if this is length 7 and this is remotely to scale, there's going to be a push outwards on these 2 joints here, on these 2 nodes here, and that is going to change the lengths of other springs. And what we might want to do is let this settle down. So we let this run and settle down until it's in a minimum energy configuration. Well, if we're looking for a minimum energy configuration, that sounds like it is an optimization task. The input is going to be the set of x1 to 5 and y1 to 5. So notice we're going to have 10 inputs. And the output is simply the total spring energy, total potential energy in the springs. And it seems reasonable that, especially with a loop type of configuration like this, there should be a way to reach 0 energy where all these springs are at their natural length. And we could find such a configuration ourselves, doing it longhand, but our challenge and our joy here is to have MATLAB do that heavy lifting for us. The only new part is going to be the idea of using more than 2 variables, using a long list of variables, and how we can easily incorporate that into MATLAB. So let's see how that can play out. First, let's get our energy calculation. If all the springs have spring constant 1, then if we want to know the total potential energy, it's going to be the sum of the spring energies. And each of those is going to be equal to 1/2 kx squared, but that is the stretcher compression squared. So we've got to be a little bit careful here because each of the lengths is a little bit different. So we're going to have, let's say, this length here, let's call it E12 plus E23 plus E34, joining these 2 joints, so the subscripts are the nodes that are being joined, E45 and E51. This is not the only way to do it, but it seems like the most transparent way to get started. And each of these have their own calculations. So E12 should be length 2. So it's whatever the length is that we actually get, squared times 1/2 times k, but k is 1. So 1/2, this is x2, y2. This location here is x1, y1. The actual length is the square root of x2 minus x1 squared plus, oh, we need more space already. You can feel this is getting mathematically complicated, though not conceptually complicated. All that square rooted minus 2. So find the length of the vector from P1 to P2, take that length, and if it's close to 2, then we have low energy. If it's far away from 2, we have lots of energy. And we just do that 4 more times. So for 2, 3, 3, 4, and so on. The key thing is we have the different lengths as part of the factor here, as part of the calculations. So this one would have a minus 2. The energy from node 2 to node 3 would have a length of 3 in it, and so on. What this gives us in the end is the ability to calculate the total amount of energy in all the springs. Well, if we have that, we can then compare different configurations and look for the one that has the lowest energy out of all of them. So how would we actually compute this in practice? What we would do is actually have a formula where we take in x as a vector, x1 to x5, and y as a vector, y1 to y5. And then we would loop over and we'd say, all right, I need to get the vector from 1 to 2. Build that. find the energy from 1 to 2 using that 1/2 times the length of V12 minus 2 squared. Then we'd say the same thing for V23. Find that as a vector. And then we'd say the energy in the spring from node 2 to node 3 is 1/2 times the difference in length between our actual length, V23, minus the length that it's supposed to be, which is 3, square that. That's our energy there. Finally, at the end, we would take our energy total, and that would be the sum of the 5 energy springs, 5 spring energies. 3, 4, 4, 5, and our last one, 5 to 1. So we can process this algorithmically pretty easily, and this is a kind of thing that we can put into MATLAB also quite nicely. That's going to be our next step.